Hello everyone. Motorized translational stage used in optics is actually very costly. So, what if we can make a normal translational stage motorized using our flexure mechanism? So, here, like from Hallmark, you can see what is the cost of a motorized translational stage, and this is the price of the normal translational stage. Similarly, from Thor Lab, which is an internationally known brand, so precision translational stage are costly, but the cost becomes threefold or fourfold when we attach a motor to it, or when we want that translational stage to be automatic with the help of some stepper motors or something. So here we are, now what we are going to do here, we are going to buy our normal translational stage, that may be precision translational stage with a resolution of like 10 or hundreds of nanometers, and then we are going to couple the stepper motor NEMA 17 specially, or 28JYB small stepper motors which are used in AC or something, or like robotics, to this costly Thorlab or Hallmark translational stage, which are precision but manual, to make it automatic. Now, what we are going to do is that we are going to demonstrate the coupling mechanism between the two, like how we are coupling the rotation of my stepper motors to the translational stage, such that like a finger, it will manually move this translational stage and will achieve that precision which is normal to the translational stage, but also make it automatic, just reducing the cost price of the whole setup. Let us imagine you have a, for example, straight plank or a stick or something which is made up of flexible material. So this is my flexible material. Now, if I put pressure from both the sides, so what will happen? This thing will actually bend like this, or it may bend in inverse way. Both things can happen. Now, suppose similarly, if I have some weak joints across this, so suppose I have a straight plank with blocks with some weak surfaces in between the two blocks. Now when I apply pressure from this side and this side together, so this thick blocks will not bend so much as this thin blocks. So what happens is that, like, it will be maybe going like this, and like this, because these thin joints will bend and thick joints will not bend as much as these thin joints. Now, if you have pre-bent the structures, like what we are doing in our flexion mechanism, so you will get something like this. So when you apply pressure from this side, it may contract, or if you apply stress in the opposite direction, it may retract, meaning either you will get something like this, or you may get something which is like this if you are retracting the pressure. So if you are putting pressure in this side, or if you are taking out pressure in this side, you may get something like this. So this whole mechanism is actually flexure mechanism, like where I am flexing the thing by either pushing from this side or either pulling from this side. Okay, so this mechanism is what we are going to use in our device, which is going to make a normal conventional translational stage to a motorized translational stage. Here is the device in which we have which is made up of cycle tires, in which we can see the 3D printed mechanism for holding to the stepper motor and also to the micrometer of the translational stage. Here in the using the cycle tire tube, we have made thick at the sides and thin at the middle, and you can see it is flexing. So as my micrometer moves to and fro because of turning, so it can adapt to that. So but if you see the rotation, if it rotates, that is hard, so it can flex in one direction only, and that is the mechanism of this type of flexure. Here we can see the demonstration of the flexure mechanism actually working. We can see the stage is moving to and fro, and it is finally connected with a Raspberry Pi, which directs it to move, and it captures a picture. It can be done in 1, 2 or 3 axis. At present it is done in 2 axis, so it can be done in 3 axis also.